Our next lesson here today is going to be on Solutions 2, and in this lesson we're going to look at the dissolving process, sort of how a substance, how a solute dissolves into a solution. We're going to talk about saturated solutions, unsaturated and supersaturated solutions, and then we're going to talk about how to do calculations on saturated solutions and saturation calculations. So first, the dissolving process. So, in a solution we have a solute which is dissolved into a solvent. And so to make the solution, the solute must be dissolved into the solvent. This is the process we call solvation. In a sense, if we have salt, we've got a little chunk of salt here, is that the molecules NaCl that are together here, remember we have our little water molecules, they're polar, they'll come in and the positive side of that will grab the negative chlorine ion, and the negative side of the water molecule grab the positive sodium ion, and so then they'll take them off and spread them out throughout the material to create this homogeneous solution, because that's what solutions are. So it has to basically, the water molecules come in, take individual ions, pull them off, or take molecules in the case of something that is, if you're dissolving something that isn't polar or isn't ionic, and spread them out. So this sort of solvation process has to happen. It has to basically take apart your solute in order to make a solution. Now, let's suppose we want to speed up this process. You have, say, I'm from Alabama, so I like making sweet tea. And so to make sweet tea, you have to dissolve a lot of sugar into the tea. And so that takes a long time sometimes. If I want to speed it up, there are three things that I can do that. The first thing you can do to increase the rate of solvation is to increase the surface area of the solute. And so if you increase the surface area of the solute, that is going to basically give you a faster rate of solvation. And so an example of this sort of makes sense, because so in this case, the more sugar molecules the water can get to, then the easier it is to take them off. It's sort of like saying this, is that, if you have to unpack books, is that if they're all in one giant box, it takes longer to do it than if they're all spread out into a bunch of little boxes, especially if you have a bunch of people that are helping, or if you have a bunch of people helping. If they're all in one box and there are a bunch of people helping, there's only one person who can get to the box at a time. And so as a result, it takes a lot longer. If they're all in little boxes, everyone can go to their own box, take things out. The same thing sort of happens in this case, is that the more different solute molecules that are available to the solvent molecules, that is, the more that surface that's available, then the faster it's going to be able to dissolve it. Basically, if you have a large chunk of something, you try to dissolve that, it's going to take a long time. So what do? You typically, if you want to dissolve something, if you have a large piece of it, you crush it up. By crushing it up is that basically you're making the particles smaller, and so giving more surface area, the water molecules can get to each little individual bit of your solute a lot faster. And so this is the first factor that will increase the rate of solvation, surface area of the solute. The second thing, which affects how quickly a solution can be dissolved, the rate of solvation, is agitation. If you want to dissolve sugar into water, then if you just put the sugar into the water and you just leave it there, it will dissolve, but it will take a long time. What you're best off doing is basically stirring it. The more agitation you do, basically what you do is you make it easier for the molecules to spread out throughout the whole substance. If you just leave it sitting there, is that those solute molecules, the solute ions, will eventually make their way through the whole substance, but at first they have to sort of work their way there. By stirring it, you distribute them a lot more evenly, and so as a result, you have a faster, goes to solution faster. It dissolves the whatever solute you're dissolving much faster. The third thing we can do is we can change the temperature of the solvent. If I have a very hot solvent, then basically the molecules of the solvent are moving faster, and if they're moving faster, then one is that you'll be able to spread out your molecules of the solute a lot quicker through the whole substance. The second thing is it's more effective at actually pulling those molecules apart. The third thing, though, with changing the temperature of the solute, the solvent, to increase the temperature of the solvent, is that whenever you do that, is that you're basically giving more energy into the system. And by having more energy in the system is that you actually can hold more solute in your solution than you could before. And that's what sort of makes this third guy somewhat unique. And so this one right here is actually more important than the other two, because while this does increase the rate of solvation, the solvent temperature doesn't only affect the rate, but also it affects the amount of solute that can be dissolved. A hotter solution will hold more solute than a colder solution for most salts. Not everything. There are a couple exceptions to this, and we'll get to one in just a second. But for most substances, for most possible solutes, the hotter the solution, the more solute it can hold. If I have water that's 5 degrees Celsius and I try to mix salt into it, NaCl, I can't dissolve as much salt into that 5-degree solution as I could into a 90-degree solution. I'd be able to get more to dissolve. If I tried to mix the same amount of salt into a 5-degree solution as I can to a 90-degree solution, I'd basically be sitting there stirring, but nothing would happen. That the solution simply won't hold as much salt at 5 degrees as it does at 90 degrees. So for each temperature, a solvent or a solution has a maximum amount of solute that can be dissolved in it, and this amount is called saturation. When a solution is saturated, it holds as much solute as it possibly can at that temperature. If you try putting more, it doesn't do you any good. So this is what we have here. Let's take a little bit more look at this guy here. Saturated solutions, as we said, saturated solutions hold the maximum amount of solute that can be dissolved in that solution. Additional solute, and I do have this sort of in quotes here, because if you add any more, it's not going to dissolve. It's not really solute, is it? Additional solute added will not dissolve. Technically, if you add more solute, some of it may actually dissolve. But here's what happens: is that, and this is sort of a little bit of an aside, is that when the solution is at saturation, that basically if you add any more potential solute to that solution, is that while some of that will dissolve, there's also some of the existing dissolved material that will then come together and fall out of solution, that will precipitate out of solution. And so basically the rate at which the solute is being dissolved is the same as the rate at which the solute is reforming into precipitate and sort of undissolving, coming back together and falling back down to the bottom here. And since those rates are balanced, they're in equilibrium, is that if you add any more solute, it doesn't do you any good. And so saturated solutions, they hold the maximum amount of solute you can get in. You can't put any more in it. And if you add more, it just won't dissolve there. So saturation point of a solvent changes with temperature, as we said. For most salts, we used them before, as the temperature increases, the saturation point increases. And typically, if we want to measure saturation point, it's generally measured in grams solute per 100 grams of solvent. For most of our solutions we'll have here, in fact for this class I believe it's all solutions we'll have here, our solvent is basically just going to be good old water. And so typically when we describe the saturation point or the saturation of a certain solution, we'd say it's the grams solute per 100 grams of water. And so let's take a look at how we do this. In order to find these saturation points, in order to find what the saturation is, we basically need a temperature solubility relationship, a temperature saturation relationship here. And so you have a colored sheet which should have this on it, and that's what we're basically going to show right here. Here is a picture of a temperature solubility chart. What this basically has is on the x-axis we have temperature in degrees Celsius. On the y-axis we have solubility in grams per 100 grams of water. And we have different curves for different materials. And so we have, sulfur dioxide down here, lithium sulfate here, sodium chloride, didn't mean to cross through it, potassium chloride, ammonium chloride, all the way up to calcium chloride up here. Different materials, and you can sort of see their curves. So for the sodium nitrate right here, here's the sodium nitrates curve going right here. Basically what this shows is these simply show that for certain temperatures, how much of that substance you can dissolve in 100 grams of water. So let's take a look at, say, lithium chloride. Lithium chloride at basically at 5 degrees. So 5 degrees is right down here. And so if we go 5 degrees up until we reach the lithium chloride curve. So lithium chloride's here. Its curve is the blue one that sort of goes along in here. So if we go from 5 degrees right here, we follow that up until we reach the curve. Then we follow it back over to the side. And so we can see that at 5 degrees, you can dissolve as much as about 72 or so, 72, 73 grams of lithium chloride in 100 grams of water. That's as much as you can do. You can't do any more. What if we went to 50 degrees? 50 degrees, right down here, we go up until we reach the curve. We reach the curve, we're going to go back over this way. And so we see that, assuming my line's pretty straight here, that at 50 degrees, you could dissolve as much as 90 grams of lithium chloride in 100 grams of water. What about at 90 degrees? If the water is 90 degrees, we follow this up to here, and then go back over to the side and read what it says over here. We see that at 90 degrees that you can dissolve as much as about 120 grams of lithium chloride in 100 grams of water. That seems a little odd, but that's actually common for a lot of things, is that you actually can dissolve more solute than you have solution, than you have solvent. And in this case, this warm lithium chloride is one of them. Looking at this whole graph, you could sort of see that for pretty much all substances on here, that as the temperature increases, going out this way, is the solubility increases, that the saturation point increases. And so that's why all the curves sort of tend to have a little bit of an upward slope going up here. There are two curves that probably should stand out to you. One of them is this sodium acetate up here that sort of has this nice curve that sort of curves upward and then has a kink in it before going out this way. We're not really going to worry too much about this kink here, but basically what it deals with is it deals with the fact that sodium acetate forms hydrates. Remember, we talked about these hydrates where basically the molecules surround water molecules and they sort of trap them inside. Is that as this dissolves, is that its tendency to make a hydrate, once the water heats up to a certain point, is this tendency to make a hydrate breaks down. And so it's acting like a hydrate before it reaches the temperature here, which looks like it's about 55, 60 degrees, somewhere in that neighborhood. And so closer to 60, I guess. My line's not very straight. After that, it sort of acts like a normal molecule, and so the curve looks a little more normal. It's a little flatter. It's not nearly as steep as it was before. And so that's the first one we have here. The second one is one that is a little more important, and that is our sulfur dioxide down here. Instead of going up, its curve comes down. It decreases. What that means is that we can not dissolve as much sulfur dioxide into a solution at 30 degrees as we can at 10 degrees. It works exactly backwards than what we expect. And the reason why that's true is because the sulfur dioxide is unique of other substances that are on this chart. And it's unique in that everything on here is a solid but sulfur dioxide. Sulfur dioxide is a gas. Gases, not just sulfur dioxide, but gases in general, almost always have solubility curves that go down as the temperature goes up. That the hotter the substance, the hotter the solution, the less gas as a solute you can mix into it. And if you think about it, this makes sense. Gases are generally moving pretty fast to start with. If you heat them up, they're going to be able to move faster. If they move faster, they can escape more easily. And if they escape, you're not fitting as much into your solution. This somewhat you'll see this is a little bit of common sense, because you know that, say, the most common case you know of having a gas dissolved into a liquid is in pop. In pop, you have carbon dioxide that's dissolved into in solution inside your pop. Typically, do you drink pop hot or cold? You drink it cold. The reason why is it can dissolve more at a cold temperature. It can dissolve a whole lot more carbon dioxide into that pop, and so it will typically be fizzier. If you take pop and you heat it up, take some pop, put it on your stove, heat it up. Put it back into something and let it cool down first. Drink it. It's going to be flat as anything. Simply at higher temperatures is that it simply doesn't hold very much. And that's true for pretty much most any gas here. So it's sort of common sense a little bit here that this works. This also is true for ocean waters. It typically is that cold water holds more dissolved oxygen, and so fish typically do a little bit better, or can be a little more inefficient with their bringing the water through their gills if they have cold water than hot water. Is that cold water tends to be oxygen rich because oxygen's a gas. And at lower temperatures, you can dissolve more gases than you can at higher temperatures. Exactly the opposite as it is for most salts. And so this is an example of how our solubility curves work, is that you can, anytime you're given an example, you just look for whatever substance this is. And for this class, everything will be something that's on this chart. I'm not going to give you anything else. There are solubility curves for temperature solubility curves for other substances. These are not all of them, obviously, but these are just the ones we're going to sit with for this class. You can find other ones online if you really need to know one, but that's what we sort of got here. Continuing onward, we've talked about saturated solutions, but there are a couple other types that we need to deal with here. First one, a solution which has less solute dissolved than the solution can hold is called an unsaturated solution. So, if a solution has as much solute as it possibly can, it's saturated. But let's suppose it has less. Let's take a look back at our previous graph here. Let's take a look at our lithium chloride. We always like that guy right there. And so let's suppose that we have 100 grams of water, and we're going to mix some lithium chloride in it. And the 100 grams of water is at 50 degrees, and we mix 50 grams of lithium chloride in. And so 50 grams lithium chloride, 50 degrees. So here's my 50 degrees right here. Here's my 50 grams lithium chloride. It meets up right here. That's well below where the curve is right there. And so I could add more lithium chloride if I wanted to. I can add it all the way up until this point right here, up until, what is that? That's about 92, somewhere about 90 grams. And so if I add only 50 to it, there's still more I could add. This basically, in this case, is called an unsaturated solution. In terms of the overall sort of picture here, is that for the lithium chloride, is anything that falls sort of below the graph, below the curve, is considered to be unsaturated. And so down here, this whole region right down here, is that would all be unsaturated for lithium chloride. If I was dealing with say, this guy up here with this sodium nitrate, then it would be everything below this curve would be considered to be unsaturated. It depends on the exact substance you've got here. So that's unsaturated here. We said before is that the things that are along the curve, right dead on that, those are ones that are saturated. So that's saturated that's right along in there. Right along the line, which would leave everything that's above the line to be something else. If we're above the line, then basically we're in this region right up here. It's going to be something even different. It's things that are up in that region right there, which are generally not possible. Remember we said that typically you could only add as much solute up to the saturation point. There are circumstances, we'll talk about in just a second, where you actually can end up with a little bit more than your saturation point. And those solutions are called supersaturated. And I know this looks fairly confusing right here, but you sort of get the general idea, is if you've added less solute than the solution can hold, it's unsaturated. If you've added just as much as it can possibly hold, it is saturated. And if you've somehow tricked the solution into holding more than it's supposed to be able to hold, it's considered to be a supersaturated solution. And so some definitions sort of continuing on that would be, is in some cases, and here's the way that we basically get a supersaturated solution. If the solution is saturated to start with, and so we start off with a saturated solution, then what we do is we cool it very, very slowly. Remember that our general graphs on these typically go up like this. If we have one where we've got a saturated solution, it's at this temperature, it's right up there. If we cool it very slowly, then what can happen is that you end up with a solution that ends up right here. That it holds more stuff than what it should be able to hold. This, it says, holds more solute than the saturation point. This is called a supersaturated solution. Normally, whenever you cool things down, if you cool it down rapidly, or you cool it down rapidly and you shake it up a fair amount, or you disturb it in some way, then what will happen is whatever's in here will just precipitate out. This amount that's sort of the difference right in there will just fall out to the bottom. It forms a solid, and it'll fall out, assuming it was a solid, that your solute's a solid. If the solute was a gas, it would just release whenever this happens. But if you do it very, very carefully, and typically you have to cool it slowly and you have to keep the solution very, very still, don't put anything into the solution, and if you do that, then it'll basically hold more solute than the saturation point. It'll stay supersaturated. But if you take this solution and you give it a bump, then what can happen is everything, the difference in here, the part that we sort of showed right up in there, that difference there will fall out, and so it'll all drop to the bottom. It'll precipitate out. So a supersaturated solution, when disturbed, will quickly precipitate the excess solute and return back to the saturation point. First time you saw this slide, you noticed what was down in the bottom right corner. The classic experiment of you take a 2 liter or 3 liter of Diet Coke and you drop a Mentos into it. and you get this nice fountain effect that we see down here in the picture. The reason why this works is that carbon dioxide that is in pop is actually supersaturated. What they do is that they put the pop under pressure, and when they put it under pressure, they basically push all that carbon dioxide into it and they get it to dissolve. Is that then whenever you release the pressure, typically, if you have a bottle of pop and you release it, is that what happens here? The carbon dioxide starts coming out. You'll start seeing bubbles start rising here. The reason why is that carbon dioxide is now precipitating out of solution. It was supersaturated, but you've now disturbed it. And so you've disturbed it, and so it starts coming out slowly here. So it's precipitating out so that it'll eventually reach its saturation point, which is basically flat pop. The particular chemistry of Diet Coke, though, means that if you drop something that has a very rough surface, and a Mentos turns out to have an extremely rough surface, and when I say rough, basically what I mean is that the roughness of the surface corresponds roughly to the type of things that carbon dioxide likes to attach to and form bubbles on. And so whenever you drop a Mentos into a Diet Coke, is that all of this carbon dioxide, which is above the saturation point, suddenly is disturbed, finds a spot for it to be able to grab onto and form bubbles, and all of a sudden, almost all of that carbon dioxide, which was supersaturated, suddenly comes out of solution all at once, and guess what you've got? You've got this nice big boom, just flies out of here in every which direction like this. This is what happens whenever you have a supersaturated solution of a gas, and all of the gas, or almost all of the gas, comes out pretty much instantly, is you get this thing where it's like, boom, this comes out here. If I had, say, a solution of a solid, then basically you would see all the crystals fall out. It almost look like snow forming as they sort of fall out slowly, and they precipitate down to the bottom. It returns to the saturation, and it will go until it returns to the saturation point, whatever that is. And so this is unsaturated versus supersaturated solutions. Let's take a look at then. We've got our saturated solutions, we've got our unsaturated, got our supersaturated. Let's see what would happen if we need to figure out exactly how much of a substance would happen for certain saturation limits here. So we're doing some calculations here. So the question is, how much KCl, potassium chloride, can be dissolved in 200 grams of 75 degrees Celsius water? So a couple things that we know here. We have potassium chloride, we have 75 grams of water. And so what you want to do is then you want to go to your chart here. So we have potassium chloride at 75 degrees. And so potassium chloride, KCl, is this guy right here. We're at 75 degrees. That's right here. We want to go up to the top, and we meet this point right here. What solubility corresponds to this? And so we take our guy over here, and we do this. We see it's right at about 50. And so what this means is that we could dissolve potentially 50 grams of KCl in 100 grams of water at the temperature the problem gives us. So we need to remember that 50 grams of KCl in 100 grams of water. And the reason why we need to know that is we're now going to go back to that previous guy here. So we said we could fit in 50 in 100 grams of water. And it's not ignoring me right here. And so what I would do is I want to set up basically a proportion. I'm going to say I've got 50 grams of KCl. Wow, that doesn't look right at all. 50 grams of KCl in 100 grams of water, H2O. So I'm going to set a proportion, and what I'm going to do is I say how much KCl can be dissolved in 200 grams of water. Is that I'm going to say I don't know how many grams KCl, I know I have 200 grams of water. At this point, all we really want to do is to solve for x. We're going to cross multiply the 200 up here, multiply the 100 up here. And so when we do that, we grab our calculators here. You get 200 times 50. And so 200 times 50 up here. And so we get 10,000. And so I get 10,000 over here equals 100x. Divide both sides by 100. And so in this case right here, I say 10,000 divided by 100, I get 100. And so x equals 100. And so I could manage to fit 100 grams of KCl into 200 grams of water at 75 degrees C. Now, to some extent, that should make sense here, because we said that from our chart that we could fit 50 grams and 100 grams of water. And so in 200 grams, I should be able to fit twice as much. And sure enough, I can. But this is basically the strategy you want to work here, is that you're going to set up a proportion using on one side the values you get off of your solubility chart. And then you use that, set up the proportion to find what you're looking for. So this is what we have for this one. So the next question, what is the smallest amount of 40 degrees Celsius water needed to dissolve 405 grams of lithium chloride? And so the first step we want to do is that we know we have water, it's at 40 degrees C, and we know we have lithium chloride. So let's look at what happens at 40 degrees C for lithium chloride. And so we want to go back to our temperature solubility graph here. And so 40 degrees C and lithium chloride. And so lithium chloride is right here. We're at 40 degrees Celsius, so we follow this guy up until we reach here. We're then going to go over, and we find that that's right at 90. And so I know I can fit 90 grams of lithium chloride in 100 grams of water. So 90 grams lithium chloride in 100 grams of water. So I say 90 grams lithium chloride in 100 grams of water. And I'm going to set this equal to what I have here. It says I want to dissolve 405 grams lithium chloride. So that's the amount of solute up here, so 405 grams lithium chloride. And I want to find how much water. Well, this is per 100 grams of water here, so I'm going to put this over x. And so once again, I'm going to do my nice little cross multiplication gig here, multiply the x up top, multiply the 100 up here. And so in doing so, I end up getting 90x over on the left is equal to 100 times 405, which is 40,500. I'm doing the math in my head right. Divide both sides by 90. So both sides by 90 here. So 40,500 divided by 90. And so in this case, I get 450. And so my x is 450. So I would need 450 grams of water to do this. Significant figure-wise, basically in this case, is that what you want to do is that the number that you sort of, there are two numbers that are important here. The first one is the one that you sort of measured off that you were given the problem, which has 3 significant figures in this case. The other one that's important here is the one you got off your graph. When we did the graph, how far did you measure it? Because really this is a case where whenever you read your graph, is that reading it determined the number of significant figures. Did you round to the nearest 10? Was this like, say, 94 and we rounded it down to 90? If it is, we only use one significant figure. Most of the time, whenever you're using the graph that at least I give you here, is that you should be able to get to the nearest gram. It may be estimated. You may not say, well, this is either 91 or 93, 92, but you still want to go to the nearest gram. And so in this case right here, even though 90 only has one significant figure, we measured this to the nearest gram here, and so that would have 2, because that's just simply how we measured it. And so our answer then should have 2 significant figures, which fortunately here it does already. And so our final answer here is that I need 450 grams of water in order to dissolve 405 grams of lithium chloride at 40 degrees Celsius. So that's how you sort of set that up right there. Let's do a couple more on this case. And so to do that, we'll go forward a couple spots. So 200 grams of saturated ammonium chloride solution at 85 degrees Celsius is cooled by 50 degrees. What mass of ammonium chloride is precipitated? Precipitated because, remember that at 85 degrees, we can hold more ammonium chloride than we can at 50 degrees. And so some of it's going to fall out unless it goes supersaturated, but presumably it won't. Most things don't. And if it does, you have to do it very slowly and do it very carefully. So we need to find how much ammonium chloride is in the solution at 85 and how much it could hold at 50 in order to find the difference. And so we're looking at 85, we're looking at 50 for ammonium chloride. And so let's take a look, 85 degrees and 50 degrees for ammonium chloride. And so we're interested in what happens at, we said, at 85 degrees and at 50 degrees. And we're talking about ammonium chloride, that's this guy right here. And so we follow this guy up to right there. That's our first one here. And following this over, we have 70. So at 85 degrees, we can fit 70 grams in 100. And at 50 degrees, we're going to follow this one up to the ammonium chloride one right here. Going over here, we have 50. So 50-50 right there. And so here's what we know. At 85 degrees, we can dissolve 70 grams of ammonium chloride. At 50 degrees, we can dissolve 50 grams of ammonium chloride. So 70 and 50 are our two guys right here. So taking a look here. Oops. So let's start off with what we've got here. Is that we know that at 85 degrees, we can fit 70 grams in 100 grams of water. Okay, we know at 50 degrees we can fit 50 grams in 100 grams of water. And we're going to set up two equations for these guys. For the first one here, we have 70 grams, and we're told that we have 200 grams of saturated ammonium chloride solution. Okay, now in this case right here, we have 200 grams of the solution, not 200 grams of the solvent. So for this one right here is that we don't know the amount of ammonium chlorides in here. That's X. But we also don't know the amount of solution. We know that we have 200 grams of the whole solution. So we'd say 200 minus X is what we have here. And the same thing is true over here, is that, actually we're going to call it Y in this case, because for the other one we don't know. It's to be 200 minus Y. Figure out how much it'll hold here. And so in this case right here, let's go ahead and see what we can do to solve this here. And so on our first one, our 85 degrees, we're going to cross multiply, same as what we did before. And I'm going to write this at the top just so we have enough space here. And so what we have here is we have 70 times 200 minus X equals 100X. And so doing this, we have 70 times 200, which should be 14,000, I believe. Once again, if I'm doing my math right. 14,000 minus 70X equals 100X. And so we'll add 70 to both sides, 70X to both sides. And in doing that, I end up with 14,000 equals 170X equals 70X. Divide both sides by 70. And so if I take 14,000, so not 70X, 170X, my bad. So 14,000 divided by 170. And so we put that in your calculator, 14,000 divided by 170. I find that I have 82.35. And so this is the amount that I start with here, is that originally I could dissolve 82.35 grams of ammonium chloride in the solution. In the second case right here is I'm going to do the same type thing I did before. I'm going to cross multiply these two guys right here. And so I'll do this one at the bottom. I know there's another problem that's down here, but we're going to sort of ignore that other problem. We'll delete it. We'll go back to it in a second. So what I have here is that I have 50 times 200 minus Y equals 100Y. Distribute this through. 50 times 200 would be basically 10,000 minus 50Y, that's a 5, equals 100Y. Add 50Y to both sides. And so I, in this case, get 10,000 is equal to 150Y. Divide both sides by 150. And so 10,000, put in your calculator, 10,000 divided by 50, and I get Y equals 200. Okay? And so I've got a little bit of a problem here, so let me take a look for just a second. I see. I apparently can't do math here. Is that 10,000 divided by 150 is very clearly not 200. So we're going to get rid of that guy right there. Is that instead it's 66.66, and so we get 66.66. And so grams here. So we started off with 82.35 grams. We ended up with 66.66 grams. And so the difference here is how much of this cannot be held by the solution anymore. It's how much precipitates out. And so we take our 82.35 and we're going to subtract from that our 66.66. And we get for our final answer 15.69 grams. Now, significant figures is we started with just one up here. And so the ones that really, since everything that we're involved here based around the 100 spot, we're going to end up with just one significant figure. So our final answer here is actually just 20 grams. So there would be 20 grams of ammonium chloride that we precipitated here. So this is how we go ahead setting that one up and doing that one. And I'll tell you this, that's about as complex as they get. That's about as complex as they get. A different type of one, though, that also does have some complexity to it is to actually figure out what the concentration of one of these solutions is. And that's what we're going to have on our next problem down here. So in this case, it says, what is the percent by mass of 40 degrees Celsius saturated sodium chloride solution? So we know we're at 40 degrees Celsius, and we have sodium chloride. So that being said, we want to go to our temperature solubility graph, Ooh, not what I meant to do. So temperature solubility graph right here. Oops. And so we said 40 degrees Celsius sodium chloride solution. And so we have sodium chloride at 40 degrees. So sodium chloride is NaCl right here. 40 degrees is right here. So that's our blue line, going up to our blue line right here. You could sort of go across here, and you see we're right about, it's a little lower than that. My line's not very good. That looks to be about maybe 30, keeping in mind that my green line's a little high because the smart board's a little off on where my mark is here. That looks to me to be somewhere in the neighborhood of probably about 37, 38. I'd say probably 38 is what I get here. So I have 38 grams per 100 grams of water is what I've got here. And so 38 per 100 is what I've got here to start with. And so let's take a look back at what we have here. And it's not listening to me again. Okay, so I know that I've got 38 grams of NaCl per 100 grams of water. And I know that because I am saturated, and I know I'm at 40 degrees. So I've got those things here. Question is, what is percent by mass? Percent by mass, if you remember the calculation for this, is basically the number of grams of solute over grams of solution. So, to do this, want to find the percent. Do we know the number of grams of solute? If we have 40 degree saturated solution, yes we do, it's 38. 38 grams. What about grams of solution? Well, we have 100 grams of water over here. That's our solvent. To find solution, we have to add those up. And so to find the solution, we do 100 plus 38, 138 grams. And so to find our percent by mass, and we got also what to forget about this, I have to multiply by 100 in both cases to get it into percent. So to do this, we'd take 38, divide it by 138, and we get 0.275 times 100, and that gives us 27.53%. Significant figure-wise, the only thing we really measured was over here originally, is that when we went to the chart, we got this was 38. And so since that's 38, that would be basically to the nearest degree, 2 significant figures. So we'll round our final answer to 2 significant figures. So what we have here is a 28% solution. So if I have sodium chloride at 40 degrees Celsius, it's saturated, it'll make a 28% salt solution.